Welcome to the course Basic Electronics and Engineering. The course code is ESCE 201. Its contact hours is three lecture periods and one tutorial. It is a 3 credit course. Myself, Dr. Shomik Poddar. I am Associate Professor of the Basic Science and Humanities Department of Institute of Engineering and Management, NewTown, School of University of Engineering Management, Kolkata. Below, this is my email. For any type of query, please feel free to contact me through this email ID. Now, today, I will be delivering the lecture 6 of the module 1, that is carrier generation and carrier recombination along with carrier injection. So before going to start, just let us review module 1, that is a semiconductor physics, which consists of the different topics. I have already discussed the previous topics, and today I will be delivering one of the most important topic just occurring inside the semiconductor, that is generation and recombination and injection of the carriers. For this type of topic, you can refer the Neiman and the Streetman Banerjee books. These are the textbooks and reference books to advance solid-state electronic devices, Pearson in Education India, and Donald Neiman Semiconductor Physics and Devices, McGraw-Hill Higher Education. Also, Simon N.Z., Yiming Lee, and Kwok K.N.G., Physics of Semiconductor Devices, John Williamson is a very, very good book for clearing the fundamentals of the semiconductor physics. So, first of all, carrier generation, what is this? We know that the carrier are nothing but the agents in the semiconductor which will carry the electric current. Just like that, we know that electrons and holes, these are the two types of the charge carriers present inside a semiconductor. Now the question arises, are they initially present inside the semiconductor, or can we modulate the generations of their semiconductor, or their concentrations will be same? So let's discuss in this session. Now, next topic is carrier recombination. Recombination means that the mixing of the positive and the negative charge carriers. So we will study also the carrier recombination and carrier injection. So basically, when carrier will be recombined, there is a devoid of this carrier. So in order to refill the carriers inside the semiconductor, or we can, if we want to restore the concentrations, or if I want to increase the concentration of the charge carriers, the carrier injection is the best method. So basically, first we will see what is the carrier, carrier generation. First, in this case, we are observing that a semiconductor materials is present. How can we say it is a semiconductor? Because there is a forbidden gap, EG, which is present in between the two energy states. The upper one is the conduction band and the lower one is the valence band. And obviously, we are applying the h nu energy. We know that h nu is nothing but a photon energy which has a wavelength of lambda and a corresponding frequency is nu. So there are two cases. One case that is shown in the left-hand side, that this photon energy is less than the band gap of the semiconductor material, and the photon energy is greater than the band gap material. So what will happen in the two cases? So before going to this complete discussion, first we will see that how this new E will be calculated. The energy of the incident photon will be given by E equals to 1.24 by lambda. What is lambda? Lambda is the wavelength of the incident light in micrometer. And 1.24, this value is coming after the manipulations of the relation of this C by lambda, means E equals to C by lambda, H nu. H equals to, we all of you know that 6.602 × 10⁻34 joules second. And nu equals to C by lambda, where C equals to 3 into 10 to the power 8 meter per second. And lambda will be given from the experimental data. So by this way, we can calculate this E. So therefore, this H nu is nothing but this E, which will be calculated using this formula, this lambda. Again, I am telling this lambda is given from the experimental experimental input data. So this H nu, when this E will be less than Eg, what will happen? And when E will be greater than Eg, what will happen? When E will be less than Eg, then we can say that this energy is not sufficient to expel the electrons from the valence band to move towards the conduction band. So there is no electron hole pair generation. Similar, but in this case, if we have increased the energy of the incident photon, and at some time, if it is greater than this Eg, automatically the electrons will get the significant or the sufficient amount of energy to overcome this energy barrier and jumps to the conduction band where they are free to move. So when the electrons will go to the conduction band, obviously there will be a corresponding vacant site created inside the valence band, and that vacant site we know that is a positive charge carriers holes. So this is a process by which we can generate this electron and the hole pair. So we can say that this process is nothing but the one side, I can say it is the injections of the carriers inside the electronic holes. Why I have told this injection? Because we know that semiconductor at 0 Kelvin, it behaves as a pure insulator. But when its temperature is increasing, suppose at room temperature, so some amount of the thermal energy is present to exert the significant force to transit the electrons from the valence to the conduction, and as a result, the holes will be generated. So this is called a normal electron hole pair generation. But if we have applied the significant amount of the photon, so it will also create some extra electrons in the conduction band, and corresponding some extra holes will be generated to the valence band. So this is a block diagram. We have seen the light is impinged on a semiconductor whose length is L in L, and this semiconductor will be excited, and thus the electron hole pair will be generated. And I can write that this light with the energy h nu greater than Eg is absorbed with the unabsorbed light intensity as a function. The depth into the semiconductor is Ix equals to I naught e to the power minus alpha x. Why I have written this expression? Because I naught is the incident photon intensity at this point, 0 point, means at the surface of the semiconductor. But the length of the semiconductor is L. So when this light will be penetrating inside the semiconductor, automatically the intensity will be decaying. So this expression variations of the electron photon intensity is expressed by the Ix function of x. X is the length of the semiconductor whose lower limit is 0 and the upper limit will be the L. So I naught e to the power minus alpha x. Alpha is called the absorption coefficient. So that means when the light is impinged on the semiconductor, some of the light will be absorbed. Because if the light will not be absorbed, then how can it will exert the electrons to the conduction band? So that's why this equation is very, very important, that if X will be much lower than the I naught, then I can think that more lights will be absorbed by the semiconductor, and what I can say that some extraordinary incidents will be happening. Now going to the absorption. So here we have plotted the alpha versus lambda. So this alpha variation with the lambda is basically the material specific. There I have listed a series of the materials starting from the 3,5 semiconductor to the normal group 4 semiconductor, gallium arsenide, then germanium, then silicon, indium phosphide, cadmium telluride, cadmium sulfide, and amorphous silicon. So amorphous silicon is a little bit different from the crystalline silicon. So amorphous silicon has a more vacant side, more of the pores. So therefore, the intensity variations will be different. So if we see that the light absorption coefficient per centimeter, so it's the alpha, it will be seen that for the germanium, it is decaying not very high intense manner. Whereas for the cadmium sulfide, it will be drastically, very sharply reduced within the 600 nanometer. So 600 nanometer is, I think that is a yellow, colored yellow. That's why it will be yellow color, because it will absorb this yellow. It will absorb the yellow light. Now, so for the germanium, it's slowly decreasing. And for the silicon, it is also decreasing, but as a very at a comparatively steeper rate than the germanium. So that means if this comparative study can tell us that if we have the two semiconductor, germanium and silicon, so we can say that as the wavelength of the light will be increasing, as the wavelength of the light will be going to the infrared, the absorption coefficient will be decaying. So as the absorption coefficient will be decaying, when the alpha will be decreased, that means the Ix will not be very much lower than the I naught, because e to the power minus, if alpha will be very high, then we can say it is nearly almost to 0. But here, in this case, we have seen for the silicon, the alpha variation is not alpha variation is very steep. So alpha is decreasing very steeply. So as alpha will be decreasing very steeply, that means alpha decreasing, so alpha value will be very much reduced. So as alpha will be very much sharply reduced, as wavelength will be increased. So I can say that if alpha value, it's a very interesting, if alpha value will be very much sharply decreasing, if the slope will be sharply decreasing, that means that means the more light will be absorbed. Similarly, for the germanium, the less light will be absorbed to create the electron and hole. Next, coming to the absorption depth. Absorption depth versus wavelength. If we see that the germanium has a lower absorption depth relation with the wavelength, whereas the silicon has a higher absorption. Higher absorption means that as we increase the light wavelength, the more light will be penetrate, the longer wavelength will penetrate the silicon. Am I right? So when the more wavelength light will be penetrated, that means its energy will be less. So when its energy will be less, so that means a less energy light will be impinged inside the silicon. So that means it will be not being helpful to create the electron and hole pair rather than the germanium. So this is one of the most interesting variation profile. Now going to the direct and the indirect band gap concept. So from that we can derive the indirect and indirect band gap concept. In direct band gap concept, the conduction band minima and the valence band maxima will be at the same position for the value of K. K is called the wave vector. It is basically coming from the quantum mechanics concept, or we can say it is a wave particle duality theory. So K is basically the wave vector for a fixed K or the same K. The minima of this conduction and the maximum of the valence will be the same point. So when it will be present, it is shown that the electrons which are going to the conduction band due to the incident photon energy, they will be directly coming back to the valence band by recombining the holes. So when they are directly recombining the holes, energy will be radiated or by emitted. So that energy is called the photon energy. That means this type of semiconductor will create some sort of visible light. Because this visible light, what I can say, because not visible, it can be seen the UV light also. Basically, the light will be increased, so the light intensity will be determined from the band gap of that semiconductor. But in case of indirect band gap semiconductor, the valence band maxima and the conduction band minima are not at the same position of the K. So as the wave vector value will be different, so to meet the holes, the electrons will traverse the path from this value K to the K value 0, and then recombine and directly fall onto the holes, and then they recombine. So this is called the indirect semiconductor. And due to this indirect semiconductor, what is happening? A very small intensity of light will be emitted. But the significant incident is happening inside this semiconductor due to the traversal of the electrons. The electrons converted its kinetic energy into the heat energy, and that heat will start vibrating this lattice of the semiconductor. So the we can say due to the electron and hole recombination, some sort of vibration will be taking place. It's called lattice scattering. And if we express this scattering as a quantized particle, it is called the phonon. So one is photon, another one is the phonon. Photon is created due to the in the direct band gap, and phonon is created to in the from the indirect band gap semiconductor. What are the examples of the direct band gap? The example of direct band gap semiconductors are the 3-5 semiconductor, that is the gallium arsenide, gallium nitride, indium phosphide, indium gallium nitride, etc. And the indirect band gap semiconductors are the silicon and the germanium. So this is the explanations of the direct band gap and the indirect band gap semiconductor. One is experiencing the phonon scattering and phonon emission, and another one is experiencing the photon emission. So direct band gap is experiencing the photon emission, and indirect band gap is experiencing the photon emission. Although a very small intensity of the photon emission will be taking place, but that is not very visible. Now, going to the magnitude of the electric field of a photon of the light. So, if the light is impinged on these materials like the gallium arsenide, indium phosphide, gallium nitride, as there is no lattice vibration is taking place, totally absorption of the light. So, what is happening? There is this is the electric field of the due to the photon of the photon incident will be varying according to this fashion. So this is the positive poles of this gallium arsenide, and the negative will be the negative poles. So in between there is an electric field will be created. So this is called the atomic dipole. So electric field will be resonates due to the photon emissions. Because why the electric field will be resonant? This is because that when the gallium arsenide will basically the electrons will directly fall to the semi holes, and therefore the electric field will be resonant. Now, in case of covalent materials such as silicon, germanium, etc., they are poor light absorbers. So as they are poor light absorbers, here we are seeing that electric field, if we are seeing is the positive and the negative pole atomic dipole, the electric field is very consistently varying. But in case of this silicon and the germanium, this incident light will not be able to polarize this silicon or the germanium. Why? This is because they are strongly attached due to the covalent bonds, and therefore it is very difficult to um, isolate the electrons and the holes within the crystal. But at the same time, a loss of heat energy will be emanated. So that heat energy will try to vibrate this crystal. So that crystal or the lattice vibration will be taking place. So that's why here we are seeing that there is a photon electric. This is a photon electric field. It will be resonates with the atom core electron cloud. But atom core electron cloud means these atoms will be atoms core electron cloud will be generated inside the silicon and the germanium, and due to this the electric field will be resonating. This is basically the band. Now different types of the recombination. This is the first one, band-to-band recombination. It is taking place in the direct band gap semiconductor. This is band-to-band generation. So when thermal energy is is impinged, then electrons will go to the conduction, leaving behind the valence band. Holes. This is called a band-to-band generation. This is adjacent recombinations. Here, thermal energy. What will happen? The electrons are uh, basically going anti-center recombination. So this is a different state where these electrons will going to here and then recombines with the holes. This is RG center generation that it is not a band to band, rather some ET means some thermal defect states are present. So these defect states will provide the RG center. This is Auger recombination. Auger recombination means that is these electrons will go. First, there is a one electron will go to the highest state of the conduction band, then slowly moving towards the minimum of the conduction band, and then another electron will position to the minimum. So what the electrons which is positioned to the minimum of the conduction band, it will can recombine with the holes. This is called the Auger recombination. Now I have already explained the band-to-band or the direct recombination. Band-to-band direct recombinations are utilized in fabricating the semiconductor devices, optoelectronic devices, lasers, LEDs. Now, recombination mechanism. Recombination mechanism needs recombination generation center recombination, which is known as the Shockley-Reid Hall recombination. What is the Shockley-Reid Hall? First carrier is trapped or localized at an unintentional defect or impurity. I have already mentioned that there is some defect state or the impurity state. So electron will not directly go to the conduction band. Rather, the electrons will go first trapped inside the defect state. Then second carrier opposite type is attracted to the RG center and annihilates the first carrier. So maybe when these situations can be assumed that when we are applying the thermal energy, not all the electrons will go to the directly to the conduction band. So some of the electrons are going to the conduction band, and some electrons are trapped inside to the defect states. So those who are trapped inside the defect state, basically what will happen, those electrons, they can recombine with the holes created to the valence band. So this process is much more faster than the band-to-band recombination. So this fast switching is used. This fast switching is basically use some devices by called the killing of EHPS. So energy loss result in a photon, single particle of your light, but is more often multiple phonon, single quantum of lattice vibration, equivalent to saying thermal energy. Again, this is the called the another phenomenon which is called the Auger recombination. Organ is OJ recombination. This requires three particles. First carrier and second carrier will be of same type. They collide instantly, annihilating the electron hole pair, first and third carrier. The energy lost in the annihilation process is given to the second carrier. Second carrier gives off a series of phonons until its energy returns to the equilibrium energy, E nearly equals to EC, this process is called thermalization. So this is another process of the Auger recombination. This is the generation mechanism, band to band, does not have a direct band gap material. Directly across the band gap mechanism that results in the Ni. Ni is the intrinsic concentration. It is basis for the light absorption devices such as detectors, solar cells, etc. This is also same thing, RG generation. This is called the impact ionization. So here, basically the electron, these bands are very steeply present. They form a tunnel-like structure. So it requires also three particles, typically very high electric field due to the steeply bent bands. Fast carriers is accelerated by high electric field or may very rarely gain enough kinetic energy on its own and collides with the lattice atom, knocking out a bonding electron, creating an EHP. EHP stands for electron hole pair. If the origin is a high electric field, this process can lead to rapid carrier multiplication, also known as the avalanching. It can be useful to fabricate the avalanche type of photodiodes. It has an upper limit set on practical electric field. Carrier injection. Carrier injection already just band-to-band carrier generation, photo generation. So I have taken the photo, each photon has an energy greater than Eg, can result an electron hole pair. So del N, del T. So this is called the rate of generation of the electron after impinging of the light will be equal to the same rate of the holes due to the light incident, which is known as the generation rate. This is G stands for the generation rate. GL means the photo generation. L stands for the light. So GL x comma lambda. X is the penetration depth or the semiconductor material depth, and lambda is the incident photon wavelength. So GLX lambda equals to GL0 e to the power minus alpha x. Already we know alpha is basically the absorption coefficient. So alpha, if alpha is small, the generation profile can be approximately constant. If alpha is large, the generation profile can be approximated at the surface. That means the maximum generation will be happened at the surface, but inside the semiconductor there is no generation. Now N0, P0 are basically the carrier concentrations when the equilibrium is present. NP is a final carrier generation in electron is the N and P is the holes. So del N is the excess carrier, excess electrons will be N minus N naught, whereas the excess hole will be P minus P naught. We have taken one variable NT, that is number of number of the generation recombination centers per cubic centimeter of the semiconductor. So N equals to, I can write del N plus N naught and P equals to del P plus P naught. So in non-equilibrium, because when you are applying some photon, the thermal equilibrium is distorted. It is not basically the prevail. So in non-equilibrium, the NP does not equal to the Ni square. But if we have injected low amount of the electron and the holes due to the low incident energy of the photon, then del P will be equals to del N, which is much less than N naught, and N nearly is the N-type material. N nearly equals to N naught. Similarly, del P will be equals to del N, which is much less than P naught. So P tends nearly equals to P naught or is a P-type material. So this is the pictorial presentation of the previous slide. So if we see that when P del P greater than P naught, that means excess holes are generated. This is called the steady state. If water equation has been applied for a long time, it is a non-steady state and it is the equilibrium. So del P under thermal generation equals to minus del P by tau P. Tau P is the minority area lifetime, where tau P equals to 1 by Cp Nt. Cp is the proportionality constant and Nt is the trap concentration. Del P, if it is negative, then generation or an increase in the carrier with time. If del P is positive, then the recombination or decrease in carriers with time. Either way, the system tries to reach the equilibrium. Similarly, del N by del T equals to minus del N by tau N, where if del N is the excess carrier, excess electron concentration, and tau N is the minority carrier lifetime. So more generally for any doping or injection case, del N del T under thermal recombination generation equals to del P by del T, which is equals to Ni square minus Np by tau P N plus Ni plus tau N P plus Pi, where Ni equals to N plus Nl plus P plus Pl. So Nl equals to Ni e to the power minus Et minus Ei by Kt, and Pl equals to Ni into e to the power Ei minus Et by Kt. And the del N by del T equals to minus del N by tau N has a solution. So the solution will be Nt equals to, this is a first order partial differential equation. So its solution will be Nt equals to N naught plus del N0 to the power minus T by tau N. So this is the graph where the del N0 is basically the equilibrium. Del N naught is the equilibrium concentration of the electron, and this is the excess carrier. It will be decaying as we are going more and more inside the semiconductor. Carrier relaxation is also achieved by through the direct recombination. So low level injection, there is a direct minor majority carrier density 1 by B N naught plus B naught. And this is for the tau delay, it's a lifetime for the direct recombination, 1 by Bn naught. For the whole series, 1 by Bp naught. High level injection, del N much greater than majority carrier density. In that case, in tau delay will be 1 by B to del N, because N naught will be replaced by the del N. Carrier relaxation, it is so OJ. Recombination involves as it is 3 particles, 2 electrons and 1 hole, or 2 holes and 1 electron. So the net recombination is described as Rg equals to minus Dn dt Cnn Np minus Ni square Cpp Np minus Ni square. And this is basically that is the tau. There is a lifetime 1 by tau OJ equals to C in N naught plus N0 del N plus del N naught plus del N. And after that, we can get the C in del N naught plus del N whole square, which can be written as Cn in N square. So that's all. Thank you very much for listening this lecture. If you have any questions, please feel free to mail me to the at this particular mail ID. Thank you very much. So this is the end of this session.